There we go. All right, perfect. Yeah, so today's agenda, we have two speakers. The first one is going to be Mehdi Bahri from the Imperial College London, and he'll be talking about binary graph neural networks and dynamic graph models. The second speaker is going to be Leo. So Leo has been attending the GNN user group for quite a long time now. And he'll be going over the simplifying large-scale visual analysis of tricky data and models with GPU, graphs, and ML. So he's the CEO of Graphistry Incorporated. We'll love to hear from him. It's a fantastic product that they're building over there. So Mehdi, with that, I'll let you introduce yourself and get started.
Okay, so thank you very much for the introduction. So my name is Mehdi. I'm doing my PhD at Imperial College. My supervisors are Stefan Zafiriou and Michael Bronstein. And today I'll be talking about binary graph networks and dynamic graph models, which is our recent work published in CVPR of this year. So should I share the screen now?
Yes, please. You can go ahead and do that. Shouldn't be any problems.
Right.
Yeah, we can see it now.
Right. Actually, what is the...
Yeah, we can see it.
Okay, yeah, it's just icons. Okay, yeah. Sorry, I just couldn't see what I was sharing. All right, so, well, I already did the introduction, so let's jump straight into it. So thank you for the invitation. First of all, I'm very glad to be presenting today. So this is our work on binary graph networks. This is a collaboration between me, my advisor, and Greg Tombal from INRIA, who works on embedded vision for satellites and has also some interest in model compression. So the work has been presented at CVPR of this year and is available on arXiv, as well as the code is on the GitHub. And we'll also be giving a demo at 2 workshops tomorrow at CVPR, Embedded Vision Summit, Embedded Vision workshop, sorry, and binary networks for computer vision. Right. So first, a little bit about model compression. So model compression is the category of techniques that aim to reduce the computational memory burden of machine learning models, often with the goal of speeding up inference on low power embedded devices, or to reduce energy consumption and increase throughput on in the data center. So many approaches have been well studied for standard deep learning, like low rank approximations, pruning, distillation, quantization, and so on, of which binarization is a special case, but they remain largely unexplored for geometric deep learning. And in this work, we focus specifically on binarization for graph neural networks. So compressing GNNs can be interesting for several applications. We can cite embedded vision, for example, onboard point cloud processing, but also possibly in the future, sensor networks and IoT. And as we said previously, data center applications like the mining of large-scale relational databases that we have in social networks or bioinformatics. So consider a general dot product operations in the neural network, like a fully connected layer or convolution. The vanilla approach to binarization is to approximate it by a dot product between quantized tensors. And usually the quantization operation we choose is a sign function. So this is fast because on binary vectors, the dot product is just a pop count on the output of the XNOR operation, which can be accelerated in hardware. But 2 important things. The first is that the output of binary dot product is not binary. The pop count is the number of non-zero bits, so it can be any integer. And a second important thing is that the training is done with floating point variables, and usually because of the nature of the sign operation, between -1 and 1. So these are 2 primers on binarization. The vanilla approach to binarization incurs some pretty substantial decrease in performance. And so research has been done to try to improve this. And the first, let's say, seminal work to achieve a substantial improvement is XNORNet, which introduces some floating point operations to reduce the quantization error. So what they do in externalnet is that instead of simply taking the sign of the tensor, they rescale it and compute a closed form solution for what constant is the one that minimizes the distance between the original floating point tensor and the rescaled binary tensor. And this is what is used to approximate the dot products. Follow-up work has replaced the closed form solution by learnable rescaling. This is the externalnet++ work. And all the developments have showed that we actually need to use nonlinear activations like ReLU and PReLU because the sign operation is nonlinear on its own, but reintroducing some nonlinear activations has some benefits as well as more advanced techniques based on distillation, reverse initialization, and so on. All of them revolve around variations of the externalnet block, which has been introduced in the paper externalnet, where they observed that the typical block for a CNN is a sequence of convolution, Batch normalization, activation, and pooling. And what they showed is that it's actually better for binary networks to do first the Batch normalization, then the activation, which is in this case is quantization, and the convolution and pooling. So for instance, we would actually add some nonlinear activation after the convolution in this case. So now that we've talked a little bit about binarization, we need to understand why binarizing GNNs is more complicated than CNNs. And first, Euclidean convolutions boil down to a single matrix product. But graph convolutions are more general than that. And often they fall into the broad class of the message passing neural networks, which I'm sure many are familiar with. But to remember, as a reminder, the feature maps for a graph element, in this case a node, are updated as a potentially nonlinear function here gamma of the previous feature map, as well as aggregated messages from the node itself, the neighbors, and the incident edges. And so this may or may not involve self loops. We may or may not have nonlinear functions of the node and edge messages, but all in all, this is a much broader formulation than Euclidean convolutions. And this shows that we need to make more design decisions when binarizing general graph convolutions than for standard CNNs. And so as a case study, we took the dynamic graph CNN model, DGCNN. So contrary to concurrent work that focus on GCN and graph attention, which are models that only involve dot product operations on node features, and especially for GCN is basically two matrix multiplications, one with the adjacency matrix and one with the weight matrix. DGCNN is actually based on the aggregation of nonlinear edge messages that depend on some edge feature defined as the difference between the feature at the node I, in this case that we want to compute the feature map for, and its neighbors. Furthermore, the model is applicable to both graphs and point clouds. For point clouds, the model relies on k-NN search in feature space to build a graph on the fly. And we essentially have two bottlenecks in terms of computational complexity in this model. The first being the dot product operations and the convolutions, and the other is the k-NN search. So we actually would like to speed up both bottlenecks. And one way to do this would be to actually have binary graph features, because we could compute binary, we could compute Hamming distances between binary vectors, which are much faster than Euclidean distances. And so in this case, we can see that it has non-trivial implications to do binarization for this model, because we have this dependence on the edge messages that may be, affected by binarization. So the first approach we took is actually to approximate the dot products as in externalnet++. So as a reminder, we approximate the dot product between two tensors by the binary node product between the quantized tensors and some learnable rescaling tensor. This keeps the output real valued, so it can be used as a drop-in replacement for the original operator, but doesn't provide a speed up for other operations besides the convolution. So it will not speed up the k-NN search, for instance. And we also use PReLU activations. But as we mentioned before, we actually want to be able to k-NN search in Hamming space because computation Hamming distance is fast. So in this case, we need to permute the order of the operations such that quantization comes last in the sequence. But the problem is, in this case, the edge features become meaningless because it doesn't actually make sense to do subtraction between binary vectors like for real valued vectors. So to find a solution to this, we actually can go back to the basics of what it means to do a subtraction. And as a reminder, a vector space is a mathematical object, which is defined as essentially the union of a group and a scalar multiplication. And the group has an operation that combines two elements such that the result of the operation is also in the group, and an identity element that we usually denote as the zero. So for instance, the usual vector space that we deal with in deep learning is just r to the power of n, which is over the field of real numbers, and uses the usual addition of n-dimensional vectors with the identity being the zero vector. The subtraction is a shortcut notation for addition with the inverse element, because one other requirement of the group is that every element has an inverse, which is defined as the element of the group, such that combining x with its inverse gives the identity. So what about binary vectors? Well, we can see them as elements of a vector space over the finite field F2, which coincides with Boolean algebra. So we have just 0 and 1 as possible coefficients. And in this case, the identity is a zero vector, and the rule of the group is the addition modulo 2, which coincides with the exclusive OR. And the additive inverse of an element is itself. So basically, what we did in this work is to replace the difference between these two node vectors by their exclusive OR, stemming from these reasons I explained before, which can be implemented as the element-wise product for floating point vectors in -1 and 1. So now the question remains where to use the Bayes normalization, because it changes the distribution of features pre-quantization, which has been observed to be important in extranet, but also especially when followed by a max pooling aggregation. Recent work on the binarization of point cloud networks has shown that it's actually quite important to ensure a balanced distribution. So in our case, the max pooling aggregation happens at the edge level, at the edge message level. So we can first aggregate, then normalize the edge messages. Or we can first normalize the edge messages, as in applying Bayes normalization here, and then do the max pooling aggregation. And in both cases, we also use p-ReLU activations. So for training, we use a 3-stage progressive distillation strategy, which is inspired by some recent paper, state-of-the-art paper on binarization for image GNNs. It's a cascaded distillation scheme that I will be describing very shortly. We also use recent advances on knowledge distillation for graph neural networks, in this case, the local structure preserving module. And we also proposed a relaxation of the Hamming distance to do quantization-aware training to compute the GNN between binary graph vectors, using this expression here, which ensures that we have a well-defined gradient. Because just like the sine function, the gradient for the Hamming distance is ill-defined, so it is problematic for training. So the 3 stages of the distillation are first to take the floating point model and to distill it into a pseudo-quantized model, which has the same architecture as the binary model, but where the quantizer is replaced by the hyperbolic tangent, and where we use floating point weights and activations. The second stage is to distill the first stage into partially quantized model, where we first binarize the activations and keep the weights real valued. And finally, we distill this into the full binary model, where we use binary activations and binary weights. Right, so a quick word about the LSP module. So LSP is a technique for knowledge distillation on graphs that incurs a loss on the distribution of similarities between node features between a node and its neighbors. So for example, here we have a node and we have its neighbors, and we compute a softmax of the similarity measures between the features of the nodes and its neighbors. And we do this for the student and the teacher. And then we have these similarity vectors, which are distributions, and the final loss is a KL divergence. So the question is, which similarity should we use? And especially for binary graph features. So one option is to do it just like for real graph features and to use the Gaussian RBF or some other standard similarity measure. But we can also try to adapt it to use the Hamming distance. And we tried this other similarity measure here. The results will be presented in the Ablation study. So in terms of performance, the baseline floating point model for GNN achieves about 92 to 93% accuracy on ModelNet 40 point cloud classification. The model that uses the Bin-Edge-Conv operator, which keeps the node features real values, it is within 2% of the baseline with binary weights. So we have a very, very close performance to the baseline with a binary model in this case. For the model that produces binary node features, so the XOR-Edge-Conv operator, we are within 1.5% of the baseline when using floating point weights. And we are within 10% of the baseline in terms of accuracy when using binary weights. So this shows that if performance is, speed is a greater concern than accuracy, then we can speed up both bottlenecks that we identified in the model by using both binary graph features and binary weights. But we can also strike a trade-off between the two by either using Bin-Edge-Conv or using XOR-Edge-Conv with floating point weights, for instance. And here we can see the baseline and the different stages of the different models. So here we have XOR-Edge-Conv models. So BF means binary graph features trained with using Hamming distance KNN search, L2 KNN search, and same here for the second variant. So we tried here the two different ordering for Bayesian normalization and the Bin-Edge-Conv model. Right. So besides computer vision applications, we also tried large-scale inductive learning. So scaling GNNs is an active area of research, and one early approach is sampling, of which a prominent example is the GraphSAGE model. So GraphSAGE samples fixed-size neighborhoods around nodes to ensure and control the complexity of the training and of the inference, and is defined by this equation here. And we binarize it as for the Bin-Edge-Conv operator. So in this case, we have, we approximated the different operations in the same way. The results are presented in this table. So we choose to evaluate the models on two node property prediction benchmarks from OGB, the Open Graph benchmark. So we chose OGB because it has standardized evaluators, which ensure reproducibility for comparisons, and also because, contrary to other benchmarks usually used in the literature like Quora, Reddit, and smaller smaller graphs, basically, the graphs in these benchmarks have high average node degree and small graph diameters, which have been shown recently to potentially exacerbate some of the theoretical limitations of GNNs with the so-called bottleneck phenomenon. In all cases, we achieved near floating point performance. Interestingly, on OGB proteins, the binary GraphSAGE outperforms the floating point GCN in terms of accuracy. And so this shows that we can combine binarization and sampling for scaling GNNs. So now onto the ablation study. In the paper, we studied the different parts of the model in details and the different factors that influence the performance. So for instance, the choice of activation function, whether we need to recenter the activations pre-quantization on top of the batch norm, as well as using the LSP on binary features with Hamming distance similarity, and the impact of the three-stage distillation, and so on. I would just go over some of the results, and for lack of space, basically. But to start with, we were able to confirm the effectiveness of the three-stage distillation strategy. So here we have the cascaded scheme compared to direct distillation from the floating point model to the binary model, and to not using distillation at all. And we can see the performance is much larger. We also were able to confirm that p-ReLU is a better choice of activation compared to not using activations or ReLU activations. And we also evaluated the need for additional recentering prior to max pooling when preceded by quantization. And so we did it both at the global aggregation step to construct the shape embedding for classifying the point cloud, as well as the edge level aggregation. So this is what we mean by global balance and edge balance. And what we observed is that with our scheme that uses batch normalization, we do not have a increase in performance by recentering the activations more by using either the mean or the median. So we also compared using LSP and not using LSP, so distilling using only logit matching or this additional structure similarity preserving module. And generally speaking, we observed an increase in performance by using this additional distillation method, but not in all cases. So as for using a similarity measure defined based on the Hamming distance for binary vectors, unfortunately, we observed lower performance than with using the standard Euclidean distance, which we conjecture to be due to poor gradients. And here, for instance, we plotted some plots of the distributions of magnitudes of the gradients between model train with LSP using the L2 distance or the Hamming distance, and we see great differences, which suggest that the gradients here are not suitable for training due to the high magnitude. So finally, we did some benchmarks on a real-world device, in this case, a Raspberry Pi 4B. So this is a low power budget ARM device using an ARM v8 architecture. We use the Lark runtime, which is based on TF-Lite, and we have 4 different optimization levels. So first, we benchmark the baseline DGCNN, so floating point network all the way. We also tried the bin edge conv operator, and we have our XOR edge conv operator using either a KNN performed with the pairwise Euclidean distances or with a unoptimized Hamming distance with some caveats. The caveats are that this version of the runtime, at the time of writing, the concatenation top key operations, which are performed quite substantially in DGCNN, were not accelerated by binarization. We denote them as incompressible operations. The second is that at the time of writing, we did not have a optimized implementation of the Hamming distance integrated within the runtime, which means that we actually took a non-optimized implementation and simulated using a conservative estimate of the speedup that ARM Neon instructions would incur on this non-optimized implementation. So nevertheless, keeping these limitations in mind, we observed a 2-time empirical runtime speedup, as well as significant reductions in memory usage and model file size, and as can be seen in this graph here. So as for future work, the first steps, I would say, would be to work on improving the stage 3 performance for XOR-EdgeConv, which means the performance of the XOR-EdgeConv models using binary weights. And we noticed that the learning rate schedule is especially important, but there could be some other improvements to make. We also think about combining this binarization method with other compression techniques for GNNs, like low-rank approximations and pruning, and also to try it on other tasks like segmentation or edge level classification, for instance. Implementation-wise, I think in order to obtain scalable GNNs thanks to binarization, there is still some work to do to develop inference frameworks that are well suited to GNNs and accelerate operations like concatenation top K, as well as in our case, integrating an optimized vectorized Hamming distance implementation. But more generally speaking, in terms of theoretical aspects of the models and the method, we are particularly interested in relating dynamic graph models with binary features to metric learning and compact hashing. So for instance, previous work on Hamming distance metric learning and binary hashing. We're also interested in the expressive power of binary GNNs. So I think one of the promising directions would be to study the theoretical properties and see if using binary weights has any consequence in terms of the expressive power of the graph filters that we're able to learn, for instance. So this is the end of my talk. Thank you for listening, and I'm happy to take any questions.
Any questions, folks? Okay, great. If you have any additional questions, please feel free to reach out to Mehdi offline, or you can, well, here's his contact information there, or you can reach him on Slack. Okay, so next we have Leo Meyerovich, and he's going to be talking about simplifying large-scale visual analysis of tricky data and models with GPUs, graphs, and ML, and all of our favorites. Leo, you have the floor.
Awesome, thanks, Wenming. All right, I'm actually going to post the link in the chat menu if I could find it. So I was thinking the beginning we could do a little poll to just meet each other, but let me find the Zoom chat menu first. We don't make it easy. Show chat, here we go. Okay, so I'm going to post the link into the private chat, or I mean the public chat. I think that should work. Let me start it. And one bit more. Let me know if folks are able to access it. And then it should show up if it's working. Okay, we got one positive. And then if it's working, we'll see it here. Okay, great. All right, we'll get back to that in a second. All right. Yeah, so hi folks. So I'm Leo, the founder over at Graphistry. We'll be talking a bit about why people like to see their data, and then how we're starting to see more and more machine learning use cases around the graph side, and kind of how all that's fitting together for us. I don't want to focus too much on Graphistry itself here. Just suffice it to say, we do cool stuff with visualization and GPUs, and we end up getting used a lot by people all over, from like security and fraud all the way to genomics, where they just want to see it. And we were kind of there from basically even before Rapids was a thing. So I'll talk a bit about that. I was kind of curious about, like, I've been attending a few of these, and I was kind of curious about who is here. And so I wanted to look at it in two ways. So one of them is I just did a quick like search for graph neural networks on Twitter, and then just ran a quick twint search. I got a little data frame with I guess like just immediate search. I think I just got like, okay, 3,000 tweets on graph neural networks. And then I used Graphistry to plot it out. This hypergraph thing is interesting. I'll get to that in a second. But let's take a look at. I think I reload the frame. Let's just try to figure out like who's actually here. Like what are we all doing here? So maybe replot that. And so yeah, and what you'll be seeing is we have the tweets, and then particularly we'll have the hashtags, the usernames, things like that. So this is just kind of like a direct graph view of some of that data. I'll try to go full screen here. Let's run the clustering a bit more. And so, yeah, like if we just like look at directly at what people are doing, and to make it a little easier, I'll just color based on the type of data that people are posting in. And so in yellow, we have the topics. So unsurprisingly, when people tweet about graph neural networks, well, deep learning and neural networks and AI, and like that's all pretty central. Like I was looking at it before, and there's some kind of interesting sub communities like all right, we have like the NIPS community and probably more academic stuff. If we just focus on topics and the people, hopefully we'll see something a little more. Okay, yeah, the people interested in publishing, sure. Yeah, we have like the NLP area, and then we can kind of see who are the NLP people. But like, you know, graphs are like, we're starting to get a sense that, okay, like graphs, at least for people data, graphs are pretty powerful. And then you can all of a sudden start finding out interesting things. Like in our case, like what I was looking at it, like kind of like the NLP community, I was actually looking at the chemistry community, where we see that the chemistry community actually shows up a bunch in the graph space. Like I don't think if I ran this search 2 years ago, we would have seen all these different communities pop up, but that was already kind of interesting to me. So yeah, I want to jump back to this poll. And so I want to just see, like, so for that first question, it looks like we have a lot of generalists here. So maybe a lot of people just doing general algorithms or creating tools. We actually do have a good number of fraud people, and kind of it's sibling to fraud in one direction is government, like imagine like crime and terrorism. And then the other side of fraud, when you're often looking at logs, it looks like we have a few like IT security people. We have a lot of NLP people, so that's kind of interesting. And then kind of as mentioned before, we have the science data, like molecules and like proteins connecting to each other to make new proteins, and then social networks kind of as we were seeing. And actually, I'm curious what the 4 other ones are. So if you're not afraid, drop it into the chat menu. I'd love to see what that is. So yeah, so like, okay, so we have a good sense of roughly who's here. So let's go to the next question, which is, you know, are you in academia? And wow, I think I got cut off. But if you're in academia, are you like trying, are you using for yourself? So that maybe you're trying it out, or you're actually successfully doing it, or are you building it for others? So this is the first 3, and kind of the same thing for industry. Are you doing it for others, or you're doing it for yourself? And then are you trying it, or is it actually in production? So I'm just kind of curious, like where's the community on graph neural networks? So definitely people trying it. So that's awesome. We actually have definitely people building tools. All right, our first person doing it in production, and not only for actually a few people doing it for production. That's awesome. Yeah, I'm sure, again, if we asked this like about a year ago, 2 years ago, like this would have been 0. So this is pretty exciting. That was actually a lot more than I was expecting ratio wise. So that's very encouraging. Okay, let's do the next one. And then when you are doing the analysis, I'm kind of curious, like what type of graph tasks. So node link classification regression is where if you have like an individual node, like a person, or an edge, like a friendship, are you classifying it to get like a discrete label, like it's like good guy, bad guy, or regression, like a score, like, oh, it's like 50% chance bad, you know, something like that. Or is it at the graph level where you're actually saying, hey, here's like a, let's say online, like it's like a behavior, like is somebody doing a conversation that's taking on the shape of trolling, or like is this like a molecule network that does something? And then would be, of course, hey, do we think that there's an edge between these 2 nodes? And embedding like classification, but hey, given a node or an edge or even a subgraph, can we like put it into like an XY space, something like that? This is actually surprising to me. I was expecting it to be like almost all like node link classification, and we do have that as one of the heaviest things, but I didn't expect graph embedding and link prediction to be as high. So that's interesting. But it looks like we have very low graph classification, graph regression. That's cool. And then of course, almost equally as important is the traditional graph stuff. And I was actually expecting that to be even higher than the rest of these. So maybe you have your own surprises here. And then I think there's one more question. Okay, so when we are doing these tasks, like how big is the graph that you're working over? And this one I could see going all, and this is another one that's kind of historically interesting. Okay, we've got some pretty big people, so billion to even 100 billion. But it's looking like over half the people are like 10 million or less. Yeah, so as that's dropping out, that's kind of interesting. And there might be a bit of a chicken and egg thing where graphs, neural networks have really struggled to scale in the graph space. Like, it's only recently that people have been pushing the bounds. So for the people who are successful, it's almost have to be smaller. But all of a sudden that's changing, and so that's kind of interesting to see how that's going. Okay, so let's jump back here. So I don't know, I found that interesting. Okay, so I want to kind of share a bit for where a lot of the Graphistry community is coming from on this. And an interesting statement is a lot of analytics nowadays runs on logs. Imagine, fraud looking at application, like imagine eBay or like any e-commerce, somebody looking at the application logs for people clicking around the site and doing interesting things. Or like using that same information, it might be a sales or marketing team. That's all on logs. But as I was shown a second, we can actually think about logs really as graph problems. And so what we've been thinking at Graphistry is really general analytics, recasting that as a graph problem. And if that's true, that means what we're talking about in this community is actually much more important than I think a lot of people realize. And so I want to kind of give like a sense for how a lot of us out in the internet land are thinking about it. So let me pull up a browser window here. So I'm sure some folks here are familiar already with hypergraphs, but if not, I'm going to kind of revisit it, but also I want to revisit it in a way that how like a lot of kind of web people in general, industry people think about it. So imagine you have like a website or like a server, and it's just generating logs of whatever is going on, like people clicking on the website, people logging into the server, maybe it's a sensor and it's just like logging what it's doing. And so we'll have like a sequence of events in a log, like maybe throw in a timestamp. So for example, on this computer, we saw one computer talk to another computer, and maybe there's like a virus scanner or something, and it triggered an alert like, oh, this computer did a leak. And maybe 10 seconds later, there's a second alert. And you can imagine like a million of these or a billion of these, like whatever amount per hour. So that is traditionally been viewed as a tabular analytics problem. How do we look at a table of events like this, where it might be pretty wide or sparse or things like that? But what's really powerful is if we can rephrase it as a graph problem. And so, and for a Graphistry user, there's kind of two ways to look at it. Like once you're used to looking at it as a graph problem, we might give an analyst kind of a pretty visualization of that log. So from a non-AI person or a non-data person, we might just give them like a pretty visualization like this, where for that same data, we have looks like we have one IP address inside of the network perimeter. We have two IPs outside. And then there's like some alert, and it looks like they both have that same alert, kind of linking them together. I'm like, okay, that's interesting. But from a graph modeling view, I'm going to kind of give you a different view of that same data. So I'm going to take that same two events and all those entities, and I'm kind of plot it a little differently. Okay. And so what we have here is the same that same data. We're actually showing two entities that I had hidden in the previous view, where we actually have those two events, like 1 and 2. And then the first event had that source IP and dest IP and that alert, and the second event also had actually a same source IP, different dest IP, and the same alert. And this is what we call like a hypergraph from not a formal view, but kind of like a visual view of it, where you have each row, like each record might be referring to multiple entities. Well, a traditional graph, you might have a source and a dest, just like each edge just has a beginning and an end. In the event land, we actually think of each edge as actually connecting multiple entities, and we actually like to include the event itself. So it's sort of like a meta, like ID pointer. And that becomes really powerful. So I'm going to kind of show. So if we go back to thinking about logs for all those, security, fraud, commercial, sales, marketing, product analytics, all those teams, that ends up being pretty powerful. So let's take a look at that. One is that for one log system, you can kind of represent all the data there. But actually, as you go across systems, let's say you have like multiple databases, some are log databases, some are relational, some might be an API. You can actually connect and normalize across all those data sources pretty naturally by just linking the entities together, maybe in this kind of bipartite way where you have those events. And it's so powerful that some kind of like you don't hear a lot of like security fraud people talking about it, but some of the bigger companies, we're getting like bits and drabs coming out. And so one of my favorite examples is Matt Swan over at Microsoft. So he used to run the Office 365 team, which is kind of at a mind-boggling scale. Like, think of like every single person with an Office 365 account, and then imagine all the logs that's generating, and then imagine the security team who has to kind of look at all the logs and kind of figure out if there's any intrusions. It's just like a lot of logs all day. And what you see him, this is actually one of our last, we put on this event, Graph the Planet. This was one of the last talks right before COVID hit, or actually as it was hitting. And it was kind of a really interesting event. So from when Matt was talking about it, he was showing on screen here a anonymized view of a few different incidents going on in the Microsoft Office 365 cluster. And one event will make like a small star, and an incident is actually a collection of logs that are somehow related, and they'll form a subgraph. And so we're seeing actually a few distinct disconnected subgraphs here. And then you're noticing color patterns. And so from we might have like maybe IP addresses one color, alerts like maybe it might be red, users might be blue, all that kind of context. Maybe like the files they're accessing are green. And then you're starting to see that there's actually like patterns to these subgraphs. And so if we go back to whether it's like security or fraud or misinformation, once you start doing these kind of like type-based colorings, it actually becomes these very rich and kind of like meaningful shapes. And so his team was kind of pretty early on doing some of this stuff. Actually, I'll get to this in a second. So like hopefully that gives you a sense of like why like we've been working with teams on this kind of stuff, and how maybe general graph neural networks connects to actually a lot of general problems. There's one aspect before I go deeper here I do want to take a pause on, which is the question of scale. And so taking a pause just on the graph neural network side and just focusing on the question of even like doing the tabular side, like say you have a node table and an edge table. That's not really a graph thing. That's just how do you have a big node table and a big edge table. I want to talk about two things. So the first thing is kind of when Graphistry started, the architecture that we had been pursuing. When we wanted to look at these really big graphs, the reason we were able to do it is we had this concept of end-to-end GPU computing built on data frames. Now there's certain technologies that we can plug in that we don't have to build our own. So I'll kind of name those that got swapped in. But conceptually, what's been going on in our space is the front end, like a browser, like whether it's a phone or a laptop, we can fit about 1 gigabyte of data into GPU memory. And then on a server, one GPU, let's say a cheap T4 might have 12 gigabytes of RAM, while A100 might have about 80 gigabytes of at the high end. And you could fit nowadays, I think, between 8 to 16 of those onto a node. And so that means what we're running in our data centers is up to about half a terabyte, or actually I think about a terabyte nowadays of GPU RAM for these graphs. That's kind of like how Spark was a revolution for normal analytics by going in memory. We're seeing the same thing with GPUs, except instead of it being just for the neural networks, because of data frames and things, we can actually do this for the full end-to-end computation. And the other note there I want to make is actually 2 bits. One is we're really focused on the case of sharing. So could you have multiple people? Let's say you have a notebook, and then your friend also, your colleague also has a notebook. Can you be sharing the same compute cluster? What happens when they're on each other? And so we're looking at things like Dask and whatever for the actual sharing of the GPUs there and try to make that automatic. And then the second thing I want to note here is when we really are working at scale, it's been really exciting working with the Rapids team at NVIDIA for working for bigger than memory, where remember about, I think a third or a quarter of the people on this in this session are actually dealing with these billion or more element graphs. What's cool is, let's say we have like, 10 terabytes of graph data. When we do something like DAS-QDF, we can actually, and I'll get to that in a bit, we can actually do bigger than memory and stream it in and out of the GPU. But also through GPU direct storage, we can actually have a parallel storage array. And so instead of kind of drinking through a straw to get at something like on S3, we can actually have like parallel connections to that and to have benchmarks almost at the level of, in theory, around 90 gigabytes per second per node. But in practice, just due to some Rapids issues, we're seeing about 2 to 4. But I think that's, again, I think we'll get that to 90 gigabytes within actually a quarter or so. So yeah, so that's kind of that notion of end-to-end, where our visual compute platform, we've been building to be actually end-to-end GPU. Like you're not just in a browser, you're actually time sharing on an end-to-end supercomputer. And then the second bit is I was using words like Dask and Rapids. Another big enabler for us has been end-to-end Arrow. And so actually, if I jump back to the notebook I was showing, in this case, for this notebook that when I was doing the Twitter stuff, it was actually pretty small. So I just did a pandas read JSON. But if it was a bigger file, what I would have actually done is switch from pandas to QDF, which is basically the same API. And I would have done QDF.read JSON. Actually, I don't think they have a GPU accelerated JSON reader, so we'd have to do their GPU accelerated CSV reader. But everything else would just work. And then when we do, bigger than the GPU can hold, we basically do the same thing, but replace QDF with DAS-QDF. And now we can do multiple GPUs or get automatic paging on one GPU, go that way. And then underneath, the key part was when we generated the visualization, when we did this dot plot, which would take the graph, send it to Graphistry to create our interactive session, we would actually send over, right now it sends over the arrow file, so it's just copying it directly to GPU memory. And we're gonna be working on letting you actually do the GPU pointer. But like, again, jumping from this view, all this stuff just was not possible when we first started. And so it's been exciting to go from having to build everything ourselves to being able to actually build on top of the Rapids community and being the sort of Rapids native graph visual analytics stack. Okay, but we're here to talk about analytics. So I wanna jump to a bit about that. And as a case study for kind of what we've been doing there, I wanna talk about Project Domino. This is a data for good effort that we helped start. If you want to learn more about it, we actually gave a keynote at DEF CON last year and at the AI Village. And basically, we saw that medical misinformation was basically subverting worldwide efforts on things like wearing masks, socially isolating, socially distancing, and vaccine hesitancy. In places like the US, that's clearly still a problem. So we've been working on open data science methods around that. And so Graph has just been so core to a lot of what we do. We've had various successes. And so one of the most recent surprises was actually for an investigation that one of our members had done even before then, which was about who was who was behind some of the main misinformation infrastructure online. And so one of our folks, Cody Webb, was actually the result of his investigation was basically the results for episodes 5 and 6 of HBO's look at who's the leadership of QAnon, for example. So the graph stuff is cool for social data, fraud data, all that. But where I want to get into here is how we actually look at it and what the methods we're using. So for the data itself, this is pretty similar to a lot of the projects Graphistry gets used for. So in this case, instead of a log store, we're using a graph store. In this case, we're looking at basically anytime somebody talks about vaccines or COVID online. And so the database right now, we have something about like, I don't know, like 500 million entities, 500 million relationships, 2 billion attributes. And so I think when we looked at it, it's like maybe think like 200 million, maybe like 50 million people on talking about COVID, and 250 million conversations about COVID, and maybe 100 million URLs that people are sharing to understand it. And so that's kind of the level of scale that we're trying to find the misinformation online. And I want to go through an example of how that works, kind of before graph neural networks, and then kind of what we're trying to do with graph neural networks. So before graph neural networks, just as a general GPU visual analytics approach to looking at a lot of data, we're using things like cuDF and for big data tables, and cuML and cuGraph for the actual analytics and machine learning. So it's end-to-end GPU. And then Graphistry, of course, uses those internally, and then we actually look at it. So an interesting technique when we're actually, for us, is when we're actually looking at and building one of these models is, and I think this is a technique true of anybody trying to look at embeddings. You're building a model, you get embedding, and you want to look at how it's doing. In this case, we used UMAP to, so let me be a little crisper here. We were looking at a bunch of accounts, and then we just computed a lot of features for those accounts. And then, tabular, continuous, all that. We ran a generic UMAP to, or you might not be familiar with UMAP, you might know TSNE or any other sort of dimensionality reduction technique. But we basically had all those columns for all these accounts, reduce them to an XY, and then we want to see, hey, are there patterns in the people we believe are doing misinformation? And then Graphistry, we just drop the table in. The thing I guess I should be clear about here is the reason we used, actually in this case, actually looks like the table is like a little bit smaller, but we were able to use cuDF and to load in bigger data. And then the GPU accelerated UMAP was actually a really big win because we can just iterate on the settings. I'm going to kind of show you how we actually use it in practice. And this is a little different from how I think a lot of people do UMAP, but it starts getting at kind of the kind of a more graph perspective of embeddings. So on screen here, we just have, by running whatever the dimensionality reduction, we have just X and Y coordinates for every account based on kind of the types of things they talk about. And it's not really that usable as is. It's cool to be able to plot it out. So that's already better than a lot of things. But the big trick we do is whenever we have accounts on screen and they're near each other, we actually add edges between them. And so you run just like a k-nearest neighbor to actually say, hey, these accounts are similar because they're the same embedding space. And then where this starts getting fun is if I then zoom out and then I start working with it, I can actually recluster based on those edges. And then I can start kind of playing with it. So for example, I'm gonna do a more of a compact layout. And here you're seeing like Graphistry on the back end is doing kind of like the iterative GPU clustering, and then kind of like Netflix screening it into the browser. And so from those 5,000 accounts that our algorithms flagged, and then those 97,000 edges that the nearest neighbors kind of connected based on similarity, I start actually getting a slightly better view of it. And so as an example, one of the first things we had done was, hey, let's just look at, for something like QAnon, which communities of misinformers is it most active in? And what we found is, like, for example, when we ask, which accounts mention QAnon a lot, we found these funny clusters. All these accounts are sort of similar, but only so based on the UMAP reduction, we believe that they're all kind of related. Maybe they're bots, maybe they're astroturfing, or like, who knows? Maybe it's part of an email, like some sort of planned campaign. But what's fun is, even though we think that almost like as a UMAP signature, that they're the same accounts, based on just, if you just looked at normal scores, you'd only think half of them were QAnon scores. So this is pretty cool. And from the Graphistry side, just being able to see all your data and putting 100,000 edges on screen is actually a big deal. And so kind of, I want to step back like conceptually for what's going on there. And when we work, as our team has been working on these problems, and we've been seeing the same at, let's say, fraud teams and security teams, basically doing the same things on their logs. Actually, I see somebody asked, are the demos available on the site? Some of these are actually, I think this is going to be recorded, and I'll have links. The talk has like links to various notebooks, so a bunch of these are. But yeah, so I was going at like, when teams are actually working with, whether you're doing a graph neural network or just graph analytics, we found that this kind of techniques have been pretty important. Like, without them, you're sort of working with blinders. And so let's say you just get the data. Being able to do the data cleaning is important. Like we're working with a telco, and they just saw that they had like an island of disconnected users. And what that really meant was, over the last year, maybe 2 years, they had a big chunk of their user data was actually, those users were connected to the main network. It's just they had dirty data in their in the beginning of their pipeline. And for the last 1 or 2 years, that data was corrupted. So being able to see your data for cleaning or exploration is kind of a big deal. What I was showing you for as soon as you have like doing actual modeling, what I showed you for UMAP, we've actually done another project, for example, in anti-human trafficking I could talk about. And there it was cool to where the model wasn't UMAP, but it was actually, we're using TensorFlow. You can imagine any BERT or whatever thing. Is kind of that same use case. A fun variant is you could actually then enrich it. So for example, once you want to show it to an actual user, another one I think we had a public talk on was for cancer genomics, where we had all the cancer protein mutations on screen. Oh, somebody asked if the interface is accessible. Actually, you can actually use it for free. We have like, yeah, so this is a user group, so I can actually go way off script here, which is fun. So if you go to graphistry.com, go to get started, you can actually get a free API key and use it within your own notebooks. So just create a free API account, and then where that'll take you, once you have the API key, you can use it from your own Jupyter notebook, kind of like I was showing you before, or if you're doing like Plotly or whatever. And then you just put in your API key, and then install it, put in your API key, and then you can start plotting. Yeah, so let's get back to what I was going about. So like, I wish I had a screenshot of the cancer stuff, but it was actually, we did this with some of the NVIDIA folks. What was cool is that we had the fuzzy links from the UMAP, but then we also, from the known cancer mutations and things like that, we actually had another set of edges from kind of like the logical known edges. Or if we're doing something like security or fraud, we would actually have like, oh, we have already, instead of just inferred alerts, we have known alerts, and you want to see them all put together. Maybe you have like red edges and blue edges, something like that. So being able to actually, once put them in the context of a real person actually looking at data, being able to do the data fusion and having that fully interactive has been pretty awesome. As a note, one thing that has been ridiculous is actually cuGraph. So I mentioned, I think, cuGraph, which is, you might know NetworkX, but cuGraph is basically, you take your data frames and then just run different graph algorithms on the GPU. Some of them are actually starting to do bigger than GPU memory, like you're seeing CATS and some others. This is fast enough that what we do in practice very often is we'll have a function decorate graph that will just run all the algorithms that are known to not crash. And then once we go into the analyst session, they're just all there. Like you just like, oh, let me color by centrality or whatever. And some of them are actually really good for dealing with visual algorithms. So I think there's like a K-core. Yeah, so K-core is one of them where oftentimes when we're looking at really big graphs, you don't want the individual nodes that aren't connected into anything. So something like a K-core analysis lets you get at really the more interesting stuff. And so by having those as dimensions for your interactive session, is really awesome. And cuGraph is fast enough that you just run all of them. I was actually hoping that I could talk today about showing you some of our new UI efforts to put that actually in tool, but that is still a work in progress, so another day. So yeah, I want to jump to like on the Graphistry side. I want to talk a little bit about what's going on with what we're seeing with graph neural networks. So when I mentioned Matt, so he's giving a talk at our user conference or community events, Graph the Planet. And this was just a year ago. And we had a panel with, I think, like 4 or 5 chief data scientists from across a bunch of like billion-dollar whatever companies. And none of them, I asked like across security and fraud, was anybody doing graph neural networks? Because, And for those companies, it was 0. And they gave a few reasons. So this is, again, right before COVID hit. What they're basically saying was, back then, none of it scaled to actual production workloads for like the type of stuff that they'd see every day. It was starting to happen, like GraphSAGE maybe it worked, but it was very difficult. And so, and the ROI, it was just like, it was unclear if they really should go down that road. And so they would still do graphs and they'd still do neural networks, but what they'd actually do is they'd run graph analytics, get all the graph scores, and then feed that through the traditional neural network. But that actually doesn't let you do fusion. And that's actually where things are starting to get more interesting. And kind of why, like, the project we're involved in, we're getting excited. So as an example, for something like node classification, where we want to know if somebody, is it a misinformer or not, or is it like a bot or not, or is it like a credit card abuser or not? That's a classification error. Or we could face it as a regression thing, where if we want a risk score from kind of the same thing. And what we're actually finding there is kind of cool is, so as a concrete example, something we're trying to do with Project Domino right now, and if you're interested, please volunteer, is we have all these URLs. So we have like, I don't know, 50 million, 100 million URLs. Some of them, those URLs, we do have scores on, and we do have classification algorithms that are kind of open source, but they only just work at the content level. Actually, I'll get to that question in a second. So those work at the content level, but they don't really. But because these URLs are getting shared, there's no way to really to include the sharing of, like, the provenance of that data or the linking structure, things like that. And so we're pretty excited about, for our first thing that we really want is for classification regression for a lot of these security and fraud problems. Can we boost the kind of the regular kind of individual alert level reasoning with that kind of rich graph structure, whether it's nearby logs or conversations, things like that, social network, whatever. And then the second thing is, this is more for the analyst rather, and maybe for kind of more of a summarization type thing. Like we think the node classification is like really the core, but then at the analyst level, one alert is like, for one immediate action. But if we go back to what Matt was showing here, where we saw different alerts really about related events forming together into an incident. Imagine somebody is trying to troll you online. It's not just one message, but it might be a conversation. Could we start understanding that thing? Or like, let's say if there's like a fraud alert or malware alert, there's probably multiple trip lines that got hit as the user was doing interactions that add up into that. Could we discover those shapes? And so for like summarization or things like that, more into the graph embedding, graph classification, things like that. But we are just in practice, we are kind of more focused on node classification for heterogeneous graphs and property graphs first. So I don't know, you're kind of seeing how we're working on some of that today. We are going to be adding some of that to our UI. If you're working specifically in the fraud space, we're actually working with another NVIDIA company, Logical Clocks. And so before we go into multiple domains, where we want to really focus on the fraud one for the neural network side. So if you're into that, also reach out there. I'm going to actually, I want to answer a question from Joanne. So I know this is a GPU group. I'd like to know if there's a comparison between graph databases and, actually, I'm not sure, is there a comp between GraphDB with, is there a company with graph database and with GPU storage? Yeah, comparison between graph database with GPU storage. Yeah, so a way I like to think about it is graph databases are really good for like somebody like Neo4j or TigerGraph is really great. They have primarily for like kind of running a lot of queries. Like let's say you have a website, and almost like inferencing. If you have a website with a lot of queries coming at the same time, could you answer each one pretty snappily? If you want to do more like analytics, so like imagine you're finding fraud or you're doing this whole graph stuff, Somebody like TigerGraph and Neo4j does have some support for that. But for example, if you look at Neo4j's graph data science library, one is it doesn't use GPUs, which is a little strange, but more differently, it doesn't use the database. It's actually separate. And so they don't really use the database for analytics. You don't really do a whole graph. TigerGraph does try to do some stuff there, but they're not GPU. And so if you want kind of CPU GPU comparisons, I'd look at the cuGraph, and it's kind of consistent with what we're seeing in the CPU space. If you look at the TPC-XBD benchmarks for Rapids versus Spark, basically we're seeing about 20x ROI improvement with GPUs. So hopefully that helps. If I ask again in the chat, I can kind of clarify further. So I'm going to share one more thing before I wrap up here. So what I was showing before with the notebooks is kind of for like a data science team, what we're doing. But what we find is as soon as a data science team wants to bring this to anybody else, problems happen where even in a data science team, people might be kind of busy. And then as soon as we want to go to like an analyst team, they have other things they need to do. And so they're really looking at ways to consume whatever we're doing. And so it's useful to look at so that basically people want an easy button because they just want to focus on the thing they need to focus on. And so as soon as we go to, let's say, more of like a scientist rather than a data scientist, they might be coding less. Maybe an investigator is really good at like fraud, but they kind of know Python, they kind of know SQL, but as soon as they do, it's a problem. And then as soon as you go more like, like line of business, like sales, marketing, trader, forget it, like, Excel, like if it's more than Excel, you're just wasting their time. And so we've actually been having really positive experiences using this, kind of the Rapids ecosystem, Graphistry, and all these companies with things like Streamlit, and Streamlit in particular, where what you're seeing on the left is sort of the easy button. So for example, in the fraud case, you can imagine putting in the name of a bank or a transaction, just like a few big buttons. And then on the right, as soon as we do the search, that's wherever like all this stuff shows up. And because Streamlit especially, Plotly as well, are part of the PyData ecosystem, we're able to just, if we want to do some like on the fly, fast interactive analytics, we could just put it in as a little Python, kind of like how you do it in a notebook. We could do it for these dashboards as well. And what we've been finding, does a lot for, within a team and definitely going across teams to sort of making this stuff more accessible. Okay, I think Joanne had a second question there. So graph supported by NLP search, it's being used on a website. Yeah, so for something like NLP search, like what we see is a difference between initial embedding and then subsequent inferencing. And so I think Rapids, for example, does have a k nearest neighbor, which would be useful for inferencing. But basically, we want to do the batching ahead of time generally, but then when we want to do at runtime the search, we want to do inferencing, and that could be CPU or GPU. Graph databases, yeah, like a lot of graph databases aren't really great at embeddings. They're great for if you're doing non-embedding based. So I think it depends on the type of search you're doing. So if you're doing neural search, you really want stuff like nearest neighbor, like like embedding. While graph might be more of on the fly compute. And their graph database like TigerGraph and Neo4j is really good at getting one node and getting a little circle around it and then letting you compute some score on that. While a neural search might actually be straight up just embedding vectors. And then that's actually fast, or k nearest neighbor, things like that. And that's a very different architecture than a graph architecture, but it could be GPU accelerated. Yeah, I hope that helps. In our case, embedding is embedding, so we can visualize both. So yeah, like stepping back, a few things here. If you want to play around with some of the stuff I was showing you, like if you just have a CSV, we recently made a CSV uploader. Just register with your username and email, not the auto sign-in. I think we have some bug on that, but then you could just drop in a CSV and without code use it. You can also get you can use your username and password actually for PyGraphistry for your notebooks or your dashboards. We're launching a bunch of stuff there, so just stop by our Slack and help out. If you're into misinformation, please volunteer. So it's actually really cool. Like now that we have like a year of all this crazy misinformation data, we're starting to actually move on to the graph neural network stuff. So go to the GitHub for Project Domino, stop by the Slack and reach out. And then more on the security fraud side. If you're doing fraud graph neural networks, we're doing some cool stuff with logical clocks. Let me put that in here. So yeah, we're working. So let's say you're at a bank or something like that. Like reach out, and then finally, for more just general stuff, just reach out if you're interested in using Graphistry in general. Like we're always happy to partner with folks and help out. Okay, and I think there's one more question. Do we have to provide a CSV JSON as input, or can we provide something like a DGL graph object? Yeah, so let's say you're using like a notebook and you want to integrate with Graphistry. So there are a couple of ways. We're working on launching. So this is going to be, you can actually do for private instances. We're working for the hub to actually get on the public one. So private instances, you can also do database connectors like Neo4j or Splunk, or anything with HTTP. Notebooks, right now the notebooks are really optimized. You could do CSV, JSON, pandas, any data frame can actually work here. So that ecosystem, they all basically turn into Arrow, so we can actually go really fast there. We are moving to add in, instead of just passing an Arrow object, to actually pass an Arrow pointer to what's on the GPU. If that's really important for what you need to do, let me know. But in practice, we've done stuff like 100 megabytes a second or a gigabyte a second, I think, with just like the Arrow CPU stuff. So as long as we just run it on the same node, it's pretty snappy. In theory, we can probably do the DGL graph object, but I'd probably want to do a DGL graph object to cuDF data frame, and then that's probably the best way to go about it. So I'd prioritize that path. And okay, yeah. Let me stop the screen share, and I know we're a bit over, but I don't know if any other questions that I can be of help with.
Hi, Leo, do you hear me?
I hear you. Yep.
Nice. So I'm Ben. I worked with you on the project Domino. So I just want to highlight that's a really awesome project, really awesome people there. And my question is, so now I'm working with a genomic company, and can you share a bit more about what you did around the cancer analysis, cancer data analysis?
Yeah, so the cancer projects, we trying to page in here. I think we were looking at, it's actually kind of tricky. We were looking at a lot of mutations, and we wanted to look at where, let's say you had a bunch of samples from a bunch of patients, and then each kind of column would be like different, did they have different mutation? And we did the UMAP trick to kind of do a dimensionality reduction of all those mutations to understand, like, lung cancer versus breast cancer, which are the mutations. And then the interesting thing about it is by using the GPU UMAP, instead of working at the, now like my ignorance is going to show, I think originally we were like, instead of working at the genome level, we were able to kind of zoom in at the protein level. Like we were just able to get more granularity because we just had that performance. The tricky part was is really wide, and normally cuDF is really dense, and so it's really meant for tall tables, like tall and thin, versus wide, because it just is currently not optimized for sparse stuff. But there are some tricks we were able to do to, and actually thank you to the NVIDIA Rapids team for helping with that we were able to do to make that work. And then the second thing we did is, I think we had EHR data. So it wasn't just like the raw genome. You can imagine auxiliary data. Once we had the UMAP to sort of connect, and we did the nearest neighbor to connect those kind of interesting proteins. And then we were able to add in the EHR, kind of like the logical data. So not the inferred edges, but the real edges. And then we had now two types of edges, like kind of what we knew the doctor wanted to look at, or what actually the clinician wanted to look at, plus what was inferred. And they were able to kind of start playing with it. Yeah, I think the notebook's actually public, so. Yeah.
Nice, thank you. That's awesome.
Yeah. Yeah, I think we're way over here. So I'll give it back to you, Wenming.
Yeah, thanks, Leo. And yeah, once again, if you have any other questions, please feel free to reach out to Leo on the Slack channel, and he's very active there. And Joe, my understanding is that you wanted to announce one of the programs that you are running.
That's right. Yeah, I'll paste here in the chat a link to our advanced applied research accelerator program that we're starting at NVIDIA. This will be a way for academics and researchers who are interested in using GPUs or already using GPUs to get access to more GPUs to help advance and accelerate the work they're already doing. So here's the link here. And there's an application on that website that you can look at and fill in if you're interested and happen to be an academic in this very small field so far. I think it's super interesting to see all the applications that are pouring out of graph neural networks and all the different ways that you can combine graph analytics with graph networks and graph databases. So anyone, please feel free to apply. We're opening up this to a pretty wide group this year. This is the first year we're running this program. So yeah, that's the short version. Great talk, Leo. Glad to hear you're getting good mileage out of all the Rapids stuff. We worked really hard to make it easy to use. So, yep.
Yeah. Anything else anyone would like to share?
A question: do you have to be an academic? Yeah, for this program there is that you have to be an academic. We have a separate program for industrial partnerships. That's a different program than this one. Yeah. And yeah, it is mostly online. Yeah, most of the interactions are online. I mean, from the last couple of years, we've gotten very good at virtual interactions. So.
Yeah, and I definitely see us doing more of both virtual and in person. Just imagine if I were to run this in Seattle.
Right. Yeah. So I'm in Austin, Texas right now.
Yeah,
so
that's right. That's right. I used to run a user group in Boulder, Colorado, and I would calculate exactly how much pizza I have to buy. It's always $162 worth, and you add 3% every year. With that, and I think definitely we should. So Joe and I should think about maybe we can add some prizes at some point for people attending. So we'll figure that out. With that, I think that's it for this month's user group. And if you have anything interesting you would like to share, definitely reach out to me on Slack, and we'll add you to the speakers for next few months. We do have a schedule. And again, I want to thank everybody for participating. I think this is the number 6, either fifth or sixth session, and we hope to keep this running and with your support, and we hope to also grow the community. And we definitely see there's I would say there's definitely been a growth in interest in GNNs, and we certainly hope that it benefits everyone, and also people get to apply them to real world problems. Again, I want to thank our speakers. I want to thank Mehdi and Leo, and I hope to see all of you again next month.
Yep.
Yeah. Thanks
Great
a lot.
job, Mehdi.
Thanks.
You.
Thanks. Great talk, Leo.
Thanks.